4 minutes after takeoff, engine number 2 on Qantas Flight 32 did not simply stop. It burst open. Metal punched through the left wing. Wiring and hydraulic systems were damaged. Fuel began leaking, and cockpit alerts multiplied. There were 469 people aboard the largest passenger aircraft in service, yet the A380 stayed in the air, turned back, and landed. How could one aircraft absorb that much damage? The answer does not begin in the cockpit. It begins inside one engine, with an oil pipe whose wall was thinner than the drawing required. The Trent 900 engine used a set of small pipes to deliver oil through its high-pressure and intermediate pressure hub. The investigation found that some of those pipes had been manufactured with a thin wall section that did not match the design specification. The machining process had removed material in the wrong place. In the engine fitted to Flight 32, normal pressure, heat, and repeated operating cycles allowed a fatigue crack to grow through that weakened wall. Nothing looked dramatic from outside. The critical failure already existed as geometry, a pipe made slightly too thin, accepted into service, and placed beside a rotating turbine. As the aircraft climbed through about 7,000 feet, the crack opened and released oil into a hot internal cavity. The oil ignited. That fire damaged the structure connecting the intermediate pressure turbine disc to its drive shaft. The disc separated, but the engine was still feeding energy into it. Freed from the shaft, the disc accelerated beyond its safe speed. Then it burst. The crew heard 2 loud bangs almost together. This was now an uncontained engine failure. High-energy fragments escaped the engine casing instead of remaining inside it. A defect measured in millimeters had become metal moving fast enough to cut through an airliner. One large fragment entered the leading edge of the left wing, crossed the front spar, passed into the inner fuel tank, and exited through the upper wing skin. It severed wiring on the way. Another fragment cut a loom beneath the center fuselage. That second loom carried backup connections for some systems already hit in the wing, so the damage did not stop at one engine or even one part of the aircraft. Electrical and hydraulic distribution were degraded, which affected systems that the fragments had never touched directly. The safety barriers had been designed as separate paths. The debris crossed those paths at different places and turned a local mechanical failure into an aircraft-wide cascade. The crew entered a holding pattern east of Singapore and worked through the procedures for the failures the aircraft was reporting. Extra pilots were already on the flight deck for a check and training exercise, giving the captain more people to divide the workload. They tested whether the damaged aircraft remained controllable, reduced weight, and prepared a landing with degraded systems. 1 hour and 46 minutes after the engine failed, Flight 32 touched down at Changi Airport. The emergency was still not over. Fuel continued to leak from the left wing, and the outer left engine would not shut down. Passengers left by stairs on the right. Firefighters finally stopped the running engine with foam about 3 hours after landing. The aircraft survived, but the investigation did not treat that as proof the design had worked exactly as expected. The damage exceeded the pattern used in the certification analysis for an uncontained engine failure. Regulators and operators inspected Trent 900 engines and removed or managed hubs with non-conforming oil pipes. Rolls-Royce added software designed to shut an engine down before a turbine disc could overspeed in a similar event, and changed how non-conforming parts were controlled. The larger lesson is simple. Redundancy must survive the paths that real damage can take. On Flight 32, an engine explosion began with a pipe wall that was too thin and ended by changing how aviation prepares for failures that refuse to stay inside one component.